A high-confidence model can still be badly wrong. ECE tells you how far confidence is from reality. This is the pattern you'll be able to implement by the end, which measures confidence calibration and reports an expected calibration error score. I'm Professor Pi, teaching AI foundations with simple Python. Models often give numbers that look like probabilities. A classifier says 90%, and you assume high certainty. But real outcomes may disagree. That mismatch is what calibration measures. In practice, you care about calibration when decisions rely on probability, not just labels. For example, a medical triage system that reports probability needs honest confidence. A miscalibrated model can mislead downstream rules, costing time or worse. Expected calibration error, or ECE, gives a single number that summarizes how far predicted probabilities are from observed frequencies. Imagine grouping predictions by score into buckets, then checking how often those buckets are actually correct. If a bucket averages 80% confidence, but only 70% of its examples are correct, that bucket is miscalibrated. ECE averages those bucket gaps with weights for bucket size. It is intuitive and simple to compute, but it depends on how you form buckets. Today, we will build a small pipeline. We will train a simple classifier on toy data, measure baseline calibration with ECE, compare binning strategies, apply a calibration method, and then quantify improvement with another metric. The goal is practical. Learn how to detect and fix overconfident probabilities using scikit-learn so you can trust probabilities more. Keep in mind, we use small synthetic data as a demonstration. The same pattern maps to your real dataset when you swap inputs. Now we will train a baseline classifier and get initial accuracy and probabilities. This snippet trains a logistic regression on a small synthetic dataset and reports a baseline accuracy. It uses scikit-learn's datasets.makeClassification to generate labeled points and model selection.trainTestSplit to create stable train and test splits. The linear model.logisticRegression object is fit on the training data, and predictions are made for the test set. The metrics accuracy score function compares predicted labels against ground truth to compute correctness. With random state fixed, the result is deterministic across runs. The printed accuracy summarizes how often the classifier gets the label right before any calibration effort. Next, we will compute expected calibration error from those probabilities. This example computes expected calibration error from the model's predicted probabilities. It defines an ECE function that bins predictions and compares each bin's average confidence to its empirical accuracy. Edges are built either uniformly or by quantiles. Then numpy.digitize assigns each prediction to a bin. For each non-empty bin, the function accumulates a weighted gap where the weight is the bin's sample fraction. The call to clf.predictProba comes from scikit-learn and supplies the needed probabilities for evaluation. Increasing n-bins tightens resolution, but may add variance. Fewer bins smooths noise, but hides local miscalibration. The printed ECE quantifies how far probabilities deviate from reality on average. Now we will compare two sensible binning strategies to see which gives a more stable reading. This code contrasts two practical binning strategies to compute ECE on the same scikit-learn predictions. The variable proba holds probabilities from clf.predictProba, and the ECE function evaluates miscalibration under uniform width and quantile width bins. Uniform bins are easy to interpret by score range, while quantile bins enforce similar counts per bin, often stabilizing per bin accuracy estimates. The best variable records which strategy gives a lower ECE for this dataset. If you increase n bins, uniform bins may get sparse in the tails, while quantile bins keep balance but may mix heterogeneous scores. The printed line shows which binning wins and by how much. Next, we will fit a calibration mapping and measure how it changes probabilities. This snippet applies Platt scaling using scikit-learn's calibration.CalibratedClassifierCV to improve probability calibration and recomputes ECE. The object is initialized with CV equals prefit to reuse the already trained logistic regression, and method equals sigmoid fits a logistic link on held-out training data to map scores to calibrated probabilities. The calibrated model cal then produces new test probabilities in proba-C, which are evaluated via the earlier ECE function using quantile bins. Switching method to isotonic fits a non-parametric mapping that can reduce ECE further when enough data is available, but risks overfitting on small sets. The printed calibrated ECE reflects how much the mapping corrected confidence errors. Finally, we will audit calibration improvement with a complementary score. This example audits reliability after calibration by combining ECE improvement and Brier scores. It recomputes raw probabilities from scikit-learn's classifier and compares them to calibrated ones using metrics Brier score loss, which measures the mean squared gap between probabilities and outcomes. The variable imper captures how much ECE decreased after calibration, giving a direct sense of better aligned confidence. Lower Brier scores generally indicate sharper, more accurate probabilities and complement ECE's focus on calibration bias. If your dataset is small, differences may fluctuate. With more data, trends stabilize. The printed values show whether calibration both reduced miscalibration and improved probabilistic accuracy. In a real system, this toy flow maps directly. Replace the synthetic data with your labeled validation set. Keep the same ECE and Brier checks, and run Platt scaling or isotonic on held-out data. Use quantile bins for stability on uneven score distributions. Recap: ECE is a weighted average of bucket gaps between confidence and accuracy. Use ECE when you care about trustworthy probabilities rather than just labels. Caveat: ECE depends on binning choice and sample size, so interpret small differences cautiously. Next step: scale this approach to a larger held-out calibration set, and try isotonic mapping when you have more data to reduce ECE further. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.